Okay, so is my mic on? Is it good? So as first, a little warning, some of the demos will use a really small font, as small as this one. So if you want to move closer, this could be useful. There's no way I can make it bigger, unfortunately. So yes, so this is me sitting in front of a screen and about to write a program. And let's say I start with a little function foo, and then when I'm writing a program, usually I have some representation in my mind of what's the current state of my program. So here I might be thinking that there is some n-byte array at the pointer called destination, and then I might write some if condition, and then when I'm writing the code in the then branch, I will think that this offset variable is now within bounds, and then maybe I'll do memcopy, and after that I will think that some subslice of my destination array now contains some data. Now, my thinking often is a little bit buggy, and then typically each time my thinking is a little bit buggy, this will lead to a bug in the program. So now, what if I had a little handy assistant that would tell me at each time while writing what I should be thinking about my program, what my current state looks like. So this is the goal of this project. But as a PL person, you have this common intuition that if you try to symbolically evaluate your programs, you will basically get to this exponential path explosion problem. And one mitigation is that you can say, okay, we look at each function separately. This helps a little bit, but still, like, symbolic evaluation usually leads to huge formulas. So this is basically the intuition why this whole thing should not work. But then, on the other hand, there's also some intuition why it should work, which is that my working memory definitely cannot fit more than half a screen of content. So the goal here is to basically simulate this thinking that I have while programming and get this to be displayed on the right half of my screen. As shown here, code editor on the left and what I call live symbolic state on the right. So I'll do a little fake demo to make it more readable of what the goal is. So say I'm starting with a little function. And then for the initial symbolic state that I want, maybe I need to give some precondition that I'm expecting to hold, and then the tool will show me on the right that indeed now this precondition holds. And then if I do some assignment, and then I want to have some kind of debug pointer, which I denote using this little blue arrow here. So let's say my debug pointer is cursor, or let's call it cursor. Debug cursor is at the beginning of the program. I can advance it, and then the tool will update the symbolic state, and I have key bindings to go back and forth with my debug cursor. And then if I write some function call which might have, or any operation that might cause undefined behavior in some corner cases, the tool should tell me that there is something that it cannot prove, that it won't work all the time. And then if I start understanding why, I can say, okay, I'll go back, and I go back even more. And notice that I can do all of this business without even having written a closing brace for this opening brace. So, and then I might want to add some test before making the function call in question, and this will update my symbolic state with this test expression, which is maybe a little too complicated, but maybe that's the right one. But at this point, maybe this is not exactly on the thing on the right is not exactly what I have in my mind, because I might have something more abstract in my mind, which might be based on some definition of what I mean by being in bounds in this particular example. So I want to add this definition, and then I want to add some special comment that says, now please think of this of the symbolic state in a slightly different way, and I want to process it so that my symbolic state matches again the way I'm thinking about my program. this might work, or maybe if the reasoning step is too complicated, the tool will ask me to prove some equivalence, and only then will it accept. And if I need to do extra reasoning, I can also add like extra reasoning steps that update the goals that I need to prove to convince the tool. So how can one implement such a thing? I basically consider two options. One would be to write a standalone tool in any programming language. This would be the more flexible solution, but the question is, does it actually show me the correct symbolic state? And in particular, with each modification that I want to make in the tool, I would have to worry, is my modification actually correct? And then the other option would be to do it inside a proof assistant. There, it puts some constraints on what I can do, and I need to use some tricks to work around these. But on the other hand, the cool thing is that I only need to trust the small kernel of our proof checker, and don't need to worry about correctness that much. So this is why I chose this approach. So now, so far I only showed you slides, which is kind of a fake demo of what I want it to look like. But now for the real demo, it actually looks almost fairly close to what I showed you on the slides. So this is Proof General running the Coq Proof Assistant, and the thing you're seeing on the left is a proof script. But actually, if I prepend this with an opening C comment, then the whole thing becomes a C file, because this one will all of this will be considered a comment, and then here this actually looks like a C function, a signature, and then come some notations that are interpreted by Coq as pre and post conditions, and then here again is actually a C code, and so on. So if I remove this opening comment, I can actually process this file within Coq, and then it's going to open some kind of proof call on the right, which can also be seen as a symbolic state. It's a little more verbose, so don't worry about the details too much. But as you can see, if I say, OK, I want to advance my debug cursor by one command, it will indeed add one more line in my symbolic state saying that my variable I is now 0. So back to the slides. How can you implement this? So I will do a little background. I apologize to all the people who use Iris, because this will be boring for you. I just want to remind you that there are strongest postcondition generators and weakest precondition generators, and WPGen of a command C and postcondition P returns the weakest precondition that needs to hold on some initial state so that the postcondition P holds after running that command. You can see two example cases of a definition of a weakest precondition generator here. And again, apologies to the Iris people, but so I have been taught WPGen a little differently, so I want to make a little quiz. So a weakest precondition generator processes programs. Do you think in forward direction or in backward direction, or does it depend? Let's do a little vote. Who thinks it is A? Who thinks it is B? OK, very good, very good. And who thinks it is C? OK, cool. So I have something to tell for all the people who think it is B, because I don't agree with you. So the thing is, the B is exactly what's taught most of the time in my perception, but I don't agree. So, but let's first see why it's actually reasonable to teach this, because let's look at the case of the sequence command for WPGen. So if you evaluate this right-hand side, what you would typically do would be, OK, we need to evaluate the arguments of this WPGen. So let's first evaluate this one. So you would evaluate WPGen of C2. This would give you the weakest precondition for C2. And you would pass this as the argument, as the desired postcondition to WPGen of C1. But actually, the thing is that this implicitly assumes that you are evaluating your WPGen in standard call-by-value evaluation order. But now, what happens if you use a different evaluation order? Lambda calculus teaches us that there are many ways of evaluating expressions. So what if we evaluate it in so-called normal order, which is just going left to right? Actually, it turns out that then we can symbolically evaluate a program in forward direction, even though we're using a weakest precondition generator. So expressed in terms of this sequence example, we would first evaluate the WP-gen of C1 without worrying about this expression here and just keeping it in place. This WP-gen of C1 returns us some side conditions that we solve right away, and only after having discharged all these side conditions will we continue with WP-gen of C2, and this actually results in being able to step through a program in a forward manner using a weakest precondition generator. The Iris people have done this for years already, but I just wanted to get everyone on the same page here. And a little other detail is that instead of using a weakest precondition generator, we can also use weakest precondition rules, where the stuff that would be returned by the weakest precondition generator just become preconditions of the lemmas or the rules that we would apply. Now, how to implement this vision of getting such a live verification tool. So the idea here is that a correctness proof of a program basically already contains the program. So instead of first writing the program and then writing the proof, which actually has pretty much the same structure as the program, we say, no, we actually directly write the proof, and the program follows from that proof. So again, representing this in a kind of fake proof assistant, let's say I have this command that I can say I want to derive some program such that weakest precondition judgment holds. So proc will actually be a hole that I want to fill in. This hole is marked using a question mark. In Coq jargon, this is EVAR. In Isabelle jargon, it's a schematic var. You can think of it just as a hole. We have initial state, which is just a variable a mapped to some value a, and we have a postcondition, a desired postcondition that says I want this variable c to contain the same variable a. And now, in order to say which program I want, I just start writing my proof. So let's start by applying the sequence rule, which you can see down here. And by applying the sequence rule, this hole up there gets instantiated with two more holes connected by a semicolon. And then it actually creates this new subgoal. And then the next thing I want to do is to do, let's say I want to do an assignment. So I apply the WP lemma for assignment with the necessary arguments to say what variable I want to assign and what expression I want to assign. And if I do this, this prog1 hole gets instantiated to this expression. And after solving some side condition, I will get to the goal for the second part of the program. And at this point in the program, the overall whole for prog is like a partial program that starts with a concrete program and then has one more hole. And then if I apply another WP set lemma, this one also gets instantiated, and the remaining thing to prove is the postcondition that this follows from the current state. And this is all a bit fake, but once you've proved everything, by just writing the proof, you also defined the program displayed in the gray box up here. Now, the only remaining question is how to make this writing of a proof feel more like writing a program. And the trick here is pretty simple. Instead of writing the proof, we add tactic notations where we say things like we want int x equals e. We want this to be a notation for apply this WP set lemma. And for each language construct, we add such a notation, and of course, a whole bunch of tricks to make it actually work. And then we can actually write code that looks like this and create a program and a proof at the same time. Now, as always, loop invariants are hard in verification. So let's go to the demo of here. I want to write a little memset program, and the insight that I want to exploit is that the symbolic state right at the beginning of right before a loop is often quite similar to the desired loop invariant. So instead of spelling out the whole loop invariant manually, I just want to say what is the diff between the symbolic state before the loop begins and the desired loop invariant. And using the Coq proof assistant here is pretty cool because it already provides me rich language to express such diffs, namely the tactic language ALTAC. So here, my current symbolic state is roughly this. I have an array at address A of some bytes bs of length n, and the key thing that I need to switch here is to turn it into this more general representation where I say I first have b bytes of I bytes of b, and then the remaining values. Then I might need to put some marker to say where my loop invariant begins. And then this one is too specific. I don't want it in my loop invariant, so I simply delete it. And now the stuff that is written here is actually usable as a loop invariant. So my tool can pick this up and prove the whole rest of the program automatically, provided that I actually give a loop invariant, a decreasing measure. But yeah, I need to give a decreasing measure, but only the diff that's needed for the loop invariant. There's some trade-offs in the design space about this. My approach is the one in the middle, and if you make this, if you make the ratings nice, you can conclude that this one is the most promising approach. There's also different ways of compiling. You can either just prepend a slash opening comment to the thing, or you can parse using Coq, go through the actual AST, because here we have a verified compiler, so you can get a more trustworthy solution. There's also some debuggable proof automation where I work hard to make sure that the system only does safe steps so that debugging the failing site conditions becomes easier. There's a whole bunch of techniques to make it actually work that you can read about in the paper. We have case studies. The one thing I just want to say is that this afternoon, Victor Fucala will present a really big case study done in this in the student research competition. And to quickly summarize my work in 3 bullet points, or actually 3 circles, my tool provides live updates as you type your code. It displays a symbolic state and is tested by a small trusted kernel. And if I place some other tools in this Venn diagram, of course, I chose it in such a way that mine is the only one in the middle. And with that, I'm done and happy to take some questions.
Yeah, we have time for a few questions.
You've showed us some pretty cool hacks. I wonder if there is say a plugin in VS Code, an extension that is dedicated to doing this. How many of the hacks can we remove, and which one remains relevant?
Oh yeah, this would be nice. This would be nice. So I didn't do VS Code. I do Emacs. I only made like one page of macros. So for instance, I can say, okay, I want to get rid of ALTAC code. So I have this thing to hide all the ALTAC code into some dots. And then, of course, if you go fancier, you could remove the opening and closing comments, and you could remove all the stuff you don't want here. I think, yeah, if you enjoy this kind of activity, I think you can do a lot of work there to make it nicer. Yeah. But on the other hand, the reason I didn't do it yet is that this is not the main problem of preventing productivity. It's more like at each step, at each thing. New program I want to try, I found out about some limitation somewhere in the tool, and I go and fix that part. So this is more a hindrance at the moment than some display issues.
Thanks for the great talk. One thing that I was wondering about during the whole talk that you sort of briefly flashed on one of your second to last slide was that I've seen a similar sort of kind of interaction loop in Daphne, where the sort of right side of the screen with the proof state gets replaced by sort of inline asserts that describe what my sort of running mental memory is. Obviously the backing of that is SMT as opposed to sort of actual tactics. I'm curious if you could speculate about why you think your tool is better or what the trade-offs are between those.
Maybe I'm not aware of the work you're referring
Daphne,
to.
the Daphne proof assistant.
Daphne, yeah, but Daphne requires you to write your assertions manually.
Sure.
And the thing is, the thing that I care about is that the tool tells me upfront what it knows about what holds.
Yeah,
that's the difference. Yeah.
Got it. Cool. Thanks.
Thank you for the very nice presentation. Sorry, I'm going to ask the question that is going to sound like reviewer 2 is asking it. But what do you consider the main conceptual takeaway of this work for the developers of other proof assistants or other DSLs embedded into proof assistants? So what's reusable?
The loop invariance as diff. That's number one. Number two, which is not exactly novel but important, is that you structure your proof automation around safe steps. And then I would say you should also look at what I call heaplet-wise separation logic. That's a cool feature I'm describing in the paper that can reuse the context.
Okay, I'll read it. Thank you.
All right, so let's thank Sam again.